So the first big announcement, you need to check Canvas for details. 10 questions due paper every Friday for the rest of the semester. Okay? Which I know isn't that long, but that means even Thanksgiving week, I want 10 questions. Okay? So you need to give me 10 questions for the rest of the semester every Friday by 5 p.m. I don't have the assignments built yet, but I will get the assignments built in there for it. You do not have to do smart work anymore. Okay? We are going to keep whatever smart work has done, whatever you've submitted into smart work for Unit 1 and Unit 2. We'll ignore Unit 3 and Unit 4. Okay? I would still highly, highly, highly encourage you to go in and at least use smart work as a place for questions. Okay? And those questions should now be different than what you see in the textbook. And what you can do is use them to write work down. Okay, so do your paper homework, open it up, and be like, well, this is how I think it should be solved. Then click Show Solution. You will get 0 points. That's fine. Okay? But by clicking Show Solution, you can at least see what the answer was and verify if you were right or wrong. Does that make sense? Okay. For those of you that aren't aware, SmartWork has been having some massive issues on the programming back end of it that they've repeatedly told me have been fixed and has clearly not been fixed. So it's going to be very tedious to go in and grade by hand Unit 1 and Unit 2 homework. I will only be grading by hand those people that did not get full points for it, so that's 90% or below on SmartWork. Right? And I will go through and look at each and every single one of your submissions and decide how many points you should be getting for it. Okay? Make sense? One of the big problems with this is the paper homework you submit will not get carefully graded. All I'm going to look for is, did you attempt to legitimately do all the way through 10 questions? So it's going to get graded a little bit stricter than the normal paper homeworks, because the normal paper homeworks, if you've shown them to me and watched me grade them, it's literally I look at it and that's it. Okay? Now I'm actually going to look at it and be like, that looks like you've completed a whole question. It's not just scattered work. Okay? You do not need to give me the question. You don't need to tell me where you found the question. Okay? But virtually everything we do in OChem involves some kind of solve, reactants to products. Showing the reactant transitioning to the product works. Okay? Providing mechanisms work. They do not have to be correct to get credit. It has to be at least a full attempt. Does that make sense? Hi.
Hey, how do you know about giving you all 60 questions for the rest of the semester?
No. Because you shouldn't have completed all questions for all the content for the rest of the semester. Okay. So one of the things I will also be looking for is, are your questions geared towards the material we're talking about, which is kind of a good point. Okay. So if you start giving me questions from first semester, how you did substitution, that's useful work, you need that, but I'm not going to count that towards the homework. So what I need to see for the homework for this Friday, next Friday gets a little bit borderline because we have the exam, but for this Friday, nucleophilic addition, nomenclature of acid derivatives, those would count. Doing nomenclature of aldehydes, ketones, doesn't count. Okay? Make it on the current content. Make sense? Okay. I do have them. Unfortunately, I have not collated and put them all together. I was hoping to get time in office hours and didn't happen. Okay. So after class, if you want to get them from me, you can. We'll talk about lab after class if you want to.
Okay.
But yeah, that's not class today. We good? Okay. Now for the exciting part. The slides, you will notice some things changing on these. For instance, I think the next slide has it. Nope, not that one. This one. We see these skips showing up. These are my notes. I've added to them. It does not appear to be helpful to be talking about the mechanism anymore. Okay, based on what I'm seeing with exam performance and everything else. So I'm pretty much cutting out mechanism discussions. Okay. Unless I'm hand drawing them in. So we will be seeing some slides pop up, some slides condensed, so if you're following along with the slides, it's not going to follow as cleanly. Okay? Let's see, go all the way back. So there we go. Gabriel synthesis is where we ended last week when we go all the way through it. The goal, the whole point of the Gabriel synthesis is to get a primary amine. That's it. Okay? If we go back and compare yields, the yield on this is actually pretty piss poor. I just happened to notice it in case somebody wanted to challenge, well, that yield is bad. Wouldn't it be better just to run the primary amine synthesis with an alkyl halide? You still generate a whole bunch of other products in that other synthesis that you wouldn't be able to remove easily. Here, the only other product is easily removed by doing acid-base chemistry. So I may get a bad or an equivalent yield that isn't very good, but synthetically it becomes helpful because I can remove the impurities. Okay? So Gabriel synthesis is there to make primary amines. That is the big goal. Okay? The ammonia and the alkyl halide, we compare down primary amine, 57%. We get the exact same yield. Okay? But again, all those other things, when we look at just the alkyl halide and the amine, all of those are virtually impossible to separate from the primary amine. Okay? So we wouldn't be able to purify it easily. Gabriel allows me that purification step, so I can actually get access to my clean product quickly. And that's its role. One of the things that I find that tends to trip people up is that the big piece that we start with the Gabriel synthesis, pretty much disappears. When we think about Gabriel, that's really all we're thinking about. We're converting the phthalimide across to the ethanamide. Kind of makes sense, or ethanamine? Is there a question? No.
Wait, sorry, can you repeat what you just said?
The part that trips people up is everybody sees the phthalimide and then looks at the ethanamine and says, well, how did you possibly break apart that ring? Like, what happened? Okay? Pretty much the bulk of the Gabriel synthesis is trash. Okay? We actually don't use it. It gets tossed, okay, or recycled out for some other thing. The primary goal is the ethanamine, and because that primary goal is pretty much sandwiched really neatly and tinily, close enough, into our reaction, okay, or into our arrow, most people tend to ignore it and kind of forget about it. You only see the big pieces, and then you freak out about it. Don't freak out. Gabriel synthesis is cool. It's got big wings, but the angel in the middle is the cool one, right? Yeah. Okay. So, Halleform. Okay, Unit 1. When we run under these conditions, what happens? Okay, the end of Unit 1, under acidic conditions, what does our ketone do? That's right, it tautomerizes to give you the enol. Okay, why is the enol special? Also right, it creates a carbon nucleophile. That carbon nucleophile can potentially go out and react with electrophiles. Right? In this case, it's going out and reacting with bromine, and we do a single substitution. Okay? We only go to the single substitution in the case of this condition because we're running under acidic conditions. If we're running under basic conditions, it happens a lot more. Okay? We can't stop it. The reason being is the product produced under basic conditions is more acidic than the starting material. When we run the reaction under this condition, under acidic conditions, okay, our product is less basic or less reactive, so it stalls after a single substitution. Okay, so that's old review stuff. Where it comes in kind of more importantly is what's known as the Halleform test, which we talked about when we first looked at this reaction, the alpha halogenation. The Halleform specifically references a methyl ketone. Okay? We have to have that methyl ketone. There are 3 hydrogens at that position. All 3 of those hydrogens are susceptible or accessible for enolate chemistry. We're running under basic conditions. Under basic conditions, we substitute all 3 of those in that alpha halogenation process. What were we doing? Bromine? This structure is now also still acidic, or still reactive, but now it's reactive as an electrophile.
How was it reactive?
Okay.
Before?
How was it reactive before is we had acidic hydrogens. Is the carbonyl still an electrophile? Yes, absolutely. Okay. But it's not electrophilic enough to be susceptible to nucleophilic attack. Okay, why not? If it gets attacked from the outset, what do we make? Exactly right, an acetal. And acetals are not stable. Acetals will, or sorry, not acetal, this is a hydrate technically. Acetals and hydrates for that matter are not stable, and so we'll revert back to the carbonyl. Okay? So while it is electrophilic, it doesn't go anywhere productive. Once we've done the full substitution, now we have the potential for something productive. That something productive is because that carbon with those 3 electronegative bromines is now able to stabilize a negative charge. The carbon can now act as a leaving group. Because it can act as a leaving group, when our hydroxide comes in and attacks, so we'll call it the OH, forming our initial hydrate, we can eject, there's our OH, CBr3. The electrons come back down and kick out the CBr3. The result here is that we would then end up with the carboxylic acid, which is a highly unstable structure, particularly in a basic environment, but that immediately negative structure that we just ejected could pick up a hydrogen, and we now generate a resonance stabilized product. That resonance stabilized product has permanently stabilized the charge on the oxygen, which now allows that to be a favorable reaction. In the very beginning, the electrophilic site was still there, but it doesn't go anywhere productive. I can't kick out a leaving group. There's no extra resonance. There's no stabilization to say that that goes anywhere useful. In the Halleform test, or the Halleform reaction, we form that carboxylate. That carboxylate is now very, very stable due to resonance. Okay? That can happen only because we've done the alpha halogenation. Kind of, sort of? Unfortunately, that's all we get. Okay? The following step can be to add acid, H3O plus, to protonate it. Typically, it is not used to make carboxylic acids. This reaction is actually used as kind of a nasty ACS test question. Okay? Which compound will give the yellow solid HCl3 when mixed with iodine and sodium hydroxide? And you'd then be given a list of compounds. Because I'm not all that horribly creative.
Is there a reason why acetals and hydrates aren't unstable?
They aren't stabilizing any charges. Okay? You don't generate, nothing about the electron density has become more stable. You aren't putting it on an atom that can hold charge better. If anything, you're removing electron density from an atom that wanted that electron density. Okay? So if we go through and look at these as possible answer choices, what do they all have in common?
They all have the ketone.
They all have carbonyls. They don't all have ketones. The first one is actually a carboxylic acid. Okay? It does have the methyl next to the carbonyl. Okay? One of the problems, which we'll discuss a little bit later, that methyl cannot be alpha halogenated. The hydrogens at that methyl position in the carboxylic acid are not acidic enough to initiate this reaction. Why? The oxygen does resonance to stabilize the carbonyl, which means I can't remove hydrogens because the negative charge can't do resonance then. It nullifies the ability to do resonance to stabilize the intermediate. Okay, so the carboxylic acid doesn't work. Okay. Well, and actually even that might be a bit tricky to evaluate. When you see a question like this, this can be very tricky to deal with. Look at some of the pieces. Iodine and sodium hydroxide. What's the most reactive thing present? Hydroxide, negative charge. Okay. Which means, what do I need to find in these? Okay. I could try to find something the most electrophilic. which would mean attacking the carbonyl. So I might say the aldehyde is the most electrophilic. Does that generate HCI3? No. Okay. The aldehyde in this case is still going to be the most electrophilic.
But you told us with this question, we're plugging off alpha hydrogen to the replication.
So we aren't looking for the electrophile. What are we looking for?
The iodine is the electrophile.
The acid.
Right?
We're looking for the acidic carbonyl, okay? Because I can look at iodine. O minus attacks iodine. What do we generate? Right? It's not a question of just finding the electrophile. It's trying to find something that's productive and useful. Is that productive and useful? IOH. Is that CHCI? 3. No. Okay. Does that have anything to do with the carbonyls? No. Okay. So it's looking for those positive and negatives. And yes, iodine's a phenomenal idea, saying it is a positive. It's not the immediate positive that I need to worry about, because that doesn't do anything that supports what I'm seeing as a possibility. Okay. So what does the OH minus have to then react with? Okay, well, again, if we're locked in under the electrophile attacks, or our nucleophile attacks our electrophiles to form, in all of these cases, hydrates. Are hydrates stable? No, they revert back to the carbonyl. I still don't generate any of these species. So what's the next most positive thing? Hydrogens. So I would need to be looking for acidic hydrogens. Well, this has an acidic hydrogen. Would the resulting base be reactive? No, because resonance stabilization. Okay? So I'd need to be looking for alpha hydrogens. I could look here and say there is an alpha hydrogen. I have to know that that is less acidic than each of these other ones. If it is less acidic, it is less likely to react. These other ones are probably better answers. Okay? Once I've done that, that puts a negative charge at the alpha position. What can that negative charge then react with? Something positive. We already identified the iodine, hook it up with the iodine. We've now done a single alpha halogenation. I've connected a carbon to an iodine. I'm now on the right path. How many times do I have to do it? 3 times. Which alpha position has 3 hydrogens for me to do substitutions? Okay. This one does, this one does. These two are now wrong. Okay. Can I remove those hydrogens as easily as I can remove the hydrogens on this other one? No. Why not? Bad resonance. Okay. Or neutralizing resonance, which means my best answer ends up coming in as this one. Okay. You can reason through using your positives and negatives, and it's one of the things I want you to do. Okay. This question is probably not on the test as a reason through. It is on the test as a, you did this in lab, it is a classification test. This reaction happens in a matter of seconds. So I can take an unknown compound, add base and iodine to it, poof, yellow solid, that's a methyl ketone. I know the identity of the compound. That's how fast this reaction happens. Okay, we talked about this kind of thing before. The Lucas test does the same thing. Okay? So they're using it as a memorization process. Did you memorize how this works? You can't possibly memorize all the possible questions. So that's why we're talking about the pieces on how you get through it. Does that make sense? Find the positives, find the negatives, connect them. You then also have to have that secondary knowledge to say that was a useful step or that was not useful. You have to apply all of those pieces. That's what makes OChem very difficult. It's either lots of critical thinking or lots of memorization. Ideally, you blend both. Make sense? Exciting. There's the mechanism. If you wanted the mechanism, we already talked through some of the pieces of it. That's the mechanism. If you're asking about the mechanism, unfortunately, I'm going to have to say no. We're going to move forward. It's straight from the textbook. That's just how tight on time we are. I apologize. Okay? hydride nucleophiles. We now have an electrophile with our carbonyls, just like we had with the aldehydes and ketones. We had the aldehydes and ketones, what did we do? Well, we reacted them with nucleophiles. Why did we pick hydride as a nucleophile? Negative hydrogen, negative carbon, negative oxygen, negative nitrogen. All of those are our kind of root functional groups or root functional atoms that can act as nucleophiles if we can make them negative. Right? So what we're concerned about in each of these chapters is what happens when I take this functional group and I do react it with a nucleophile. Where do I get that nucleophile? What happens? So if I add sodium borohydride to this, what's going to happen? Well, what happened when I took it with a ketone? Sodium borohydride is effectively what? A negative hydrogen. The negative hydrogen goes in and attacks. What does it break? The pi bond. The result being a negative oxygen. Is that a favorable reaction? What did I start with? Pi bond and no charge. We started with a charge. We started with a negative hydrogen. What did I end with? Negative oxygen. Is this reaction favorable? Yeah, it's really favorable. We're taking an atom that doesn't want to hold the charge because it is insanely small, and I'm now putting it, and low in electronegativity, and I'm putting that charge on an atom that is not only bigger, but higher in electronegativity. It can stabilize that charge. Okay, so that is a favorable step. Is there anything else that's potentially reactive within that structure? Well, all I've got is that negative oxygen. Could the negative oxygen come back down to reform the pi bond? So one option, which is a reasonable answer, is that it exceeds the octet. And you're saying it exceeds the octet not just because it exceeds the octet, but because... let's try it with the next one. Take a look at the bottom one. Negative hydrogen does what? Attacks, breaks the pi bond. The result? Negative oxygen, right? Hydrogen, yeah? Can these electrons come back down? Whoa. We just went from no, it can't happen, or silence, to a chorus of yeses. What all of a sudden changed that allow you to go, oh, well, of course it can come back down. It's still exceeding the octet. It has to do with the rest of the structure. There's a leaving group. In the top case, we can say it exceeds the octet. It's still exceeding the octet down here. Okay? It's that secondary piece. It's that extra piece that you have to be acknowledging and stating. In the top case, there is no leaving group. Why is there no leaving group? So the explanation I got is carbon can't stabilize negative charge, so I can't find negative carbons.
It's not as stable as a negative oxygen.
Okay. Our comparison is always back to the reactive thing. Carbon can't stabilize the negative charge as well as oxygen, which is why carbon can't act as a leaving group. When we shift to this one, what happens? Now all of a sudden you're saying the electrons can be ejected. Why can those electrons come back out? Because chlorine can stabilize the negative charge better than oxygen. Why? It's bigger. Up here, carbon can't stabilize the negative charge as well as oxygen because it's less electronegative. Notice we're using the exact same rules we've been using all the way through the semester on ranking stabilities of charges. That's why we've got them. So cool. We just went through and created a product. Is this the product of the reaction? That looks nice and stable, right? So that should be the end of it. Oh, but it's not, because we have what functional group? An aldehyde And what does sodium borohydride provide? A bunch of negative hydrogens. Is the aldehyde still reactive? Yes. What happens? It reacts again according to the stuff from the last unit, directly shown above, and we end with the alcohol. We can't actually stop it at the aldehyde, at least with sodium borohydride. It'll go all the way through to the alcohol. Okay? Some of that has to do with the reactivity of sodium borohydride. It's not easy to control the hydride concentration in there. Why might it not be easy? Right, there's 4 hydrides, right? Doesn't it react 4 times? How reactive is that hydride? Very reactive, which means when I go to measure it out in the open atmosphere, what is it potentially reacting with?
Everything.
I can get a little bit better than everything, but yes. Stuff in the surrounding atmosphere, like water. When you exhale, you've got water. I know it was a bad example. But you've got water in the atmosphere with acidic hydrogens. Those acidic hydrogens can react with some of the hydrides, albeit slowly, but it does react. So that if we measured this out to be exact equivalents to try and get here, we're going to get a bad yield. We need an excess of the hydride. The instant we put in an excess of the hydride, what happens? Well, crap, I start reducing all the way down. Kind of make sense? So the way we fix that is just make sure we've got enough hydride to completely do the whole thing. Then we don't got to worry about it.
So that's because you said that was super strong, so Dieball would stop at the aldehyde.
We'll get to that, and Dieball. But yes, we'll get to that. There were 2 hydride sources, sodium borohydride and lithium aluminum hydride. Okay, we've got a nice little table here from your textbook that shows how they react. Okay, starting with our acyl chloride, the anhydride, ester, acid, and the amide. Okay, sodium borohydride, lithium aluminum hydride. What do you notice as a difference between those 2 columns? Lithium aluminum hydride reacts in every single case. Sodium borohydride stops reacting. Okay, we don't get a reaction with the acid. We don't get a reaction with the amide. Okay? If we continue to look, it actually says the ester is very slow. It's actually so slow that if I want to reduce the ester, I don't use sodium borohydride. Okay? It's not a useful reagent for that step. Okay? Why would that be the case?
You mentioned, I think, in the previous one, I don't remember when, but you said that with the electronegativity, boron is closer to hydrogen versus aluminum that's farther than hydrogen.
Yep.
Therefore, lithium aluminum hydride is a stronger reducing agent than the other.
Yeah, so what we talked about in the previous unit was that ranking of lithium aluminum hydride versus sodium borohydride. One of the first analogies we went after was the boron versus the aluminum. Boron has a higher electronegativity than aluminum because it's higher on the periodic table, right? Which means the bond between the hydrogen and the boron in sodium borohydride is actually a stronger bond. Because it is a stronger bond, the hydrogen is less negative. If it is less negative, it will be less likely to react. Lithium aluminum hydride, because of a larger difference in electronegativity, is now more likely to react. Okay? There's another factor that contributes to this. Okay? That other factor has to tie in with the reactivity difference between our ketones, aldehydes, and acyl chlorides. Okay? And for that matter, our esters. So if we take a look at the above reaction, we're starting with an ester and a ketone in the same structure. When we react it with sodium borohydride, what happens? Only the ketone is reduced. The ester is not touched. Okay? Previous slide, this is, again, textbook, straight from the textbook, says it should reduce. Okay? Why does it not reduce? It's only been 5 minutes. If we run the reaction for a very short time, we don't expect the ester to reduce. Okay? If we increase the amount of time, we can increase the likelihood that the ester gets reduced. Okay? Why would I then not use lithium aluminum hydride? So I use lithium aluminum hydride, they're both reduced.
Hold on. From what I
I want some selectivity. I don't want to reduce the ester. I only want to reduce the ketone. Right? So I'm allowed to differentiate based on the selection of the reagent. Sodium borohydride will only react with part of the molecule, but not the other. It's a selective reagent. Yes?
You also mentioned that lithium aluminum hydride is explosive.
Lithium aluminum hydride can be more explosive. It's not that explosive, but it can be more dangerous to work with because it's a more active hydride. So we want to be a little bit more careful with it. Okay?
So the sodium borohydride is more selective than lithium aluminum hydride?
Yes.
So lithium aluminum hydride is stronger.
Yes.
Is Dieball the same strength?
We aren't even at Dieball yet.
I need to know.
Okay? So back to my question. What is the difference between a ketone, aldehyde, acyl chloride, and an ester? Well, if we look at the acyl chloride, what might we expect its reactivity to be? High or low? Why high? Okay. One option is to say the chloride's a good leaving group. That's kind of hand-wavy, and it'll work for a little bit, because if I compare the acyl chloride to the anhydride, chloride's better than that acid portion, right? So we could say it's a better leaving group. So we could use that with all of our acid derivatives. Where does that argument then fall apart? Aldehydes and ketones reacted. Esters did not. If your argument is leaving group ability, isn't an oxygen's leaving group ability better than a carbon's? Ooh, leaving group ability doesn't work to explain this. What is the difference? Nope, because the electrophiles, yes. Why is the electrophile, why is this the most electrophilic and this the least? That's least.
Pulling some of the electrons away from the carbon.
Okay, pulling the electrons away. So the argument that he's making is that chlorine's more electronegative. Is oxygen more electronegative, pulling electrons away? Yeah. Isn't oxygen more electronegative, pulling electrons away than the carbon? Wouldn't that still make the ester more active?
Is charge a factor?
It's not charge. Before we start looking at induction, we have to be concerned about resonance. When it comes to the ester, we have a resonance stabilization. Don't we get resonance stabilization then with the anhydride? Doesn't that stabilize the electrophile? If the electrons go that direction, what happened to the other side? It became more positive. There isn't a resonance stabilization in the case of the anhydride. That's why the anhydride can react so much more. When we look at the chloride, doesn't the chloride have electrons? Couldn't it theoretically stabilize? How often do you like to see chloride with two bonds? I don't know is not a bad answer. It doesn't. Okay? Particularly two bonds to the same atom. Even when we see the bromonium and the chloronium, those are really half-butted answers to explain what we end up seeing as an observable. We aren't really seeing a double bond there. Chlorine's too electronegative, does not want to stabilize by donating electrons in, so it's placed up at the highest end. Our aldehydes and ketones do not have that resonance ability that the esters, the acids, and the amides have, which means they are more reactive than our acids, esters, and amides. They are less active than the other ones because the other two up top have a strong electronegative effect with the acyl chloride and have a strong resonance, counter-resonance argument with the anhydride. So looking at the reactivity of all of these functional groups at the same time is a really important thing to evaluate because that's what allows you to differentiate why different reagents or reducing agents react at different rates. Okay? Why does lithium aluminum hydride then react with everything? Why would so sodium borohydride doesn't react with the ester well. So if we drew a line here, sodium borohydride does all of these. Lithium aluminum hydride does all of these. Why would lithium aluminum hydride do everything? Okay, we're going to ignore that I do. Actually, look at that. Here we go. Lithium aluminum hydride, we already explicitly stated, was a stronger reducing agent. Even it will overcome that resonance stabilization effect. Okay? So it will react with all of those. You can get more nitpicky into the details behind that, but I'm going to argue we shouldn't worry about it. We just need to know it. Which means our answer for this becomes, what is the lithium aluminum hydride reacting with? The carbonyl. So is it reacting with this? No. So what should we do? Leave it. Whoa, God. We should leave it alone. Okay? Is it reacting with the nitrogen? Okay, and this becomes tricky because if we think about all of our reductions, for instance, if this was the acid, right, let's make it the ester, and we did the reduction, what would we end up with? We'd end up with our OH, right? Okay. Should I end with an OH or should I keep the N? And really what's going to drive that is looking at this state. Okay. So I've done one nucleophilic addition of hydrogen to that. Okay. So now the question is, what would be my leaving group? So we might consider that the nitrogen would go down and kick out to form N minus. What's the other option? Kicking out the carbon stuff. There's another option. Doesn't the nitrogen have a lone pair of electrons? Yep. It could donate in, kicking out, and you might be like, oh my God, O minus 2, that's insane. It's true. Okay? The question becomes why. Okay? What you will end up forming is a very strong bond between the lithium and the oxygen, so that you end up not really kicking out O minus or O minus 2. You end up just kicking out O minus. And I said, well, that's still a negative charge. Well, which is better as a negative, oxygen or nitrogen? Oxygen, which means which one's the better leaving group? The oxygen, which means my first stage is to form the imine, which can then, because I now have a polar pi bond, that can be attacked by another hydride. Wow, eraser. And I end up doing the full reduction down to the nitrogen instead of the oxygen. Because nitrogen is a better nucleophile, we're leaving the nitrogen attached to the carbon. Do not eject it. So when we do a reduction of amides, we end up with amines. For those of you that don't believe me, sorry. Oh my God. Take a look at the amide. What do we end with? There it is, the amine. Okay. Nitrogen is a better nucleophile than our oxygen. Will leave the nitrogen connected to the carbon. The oxygen would rather be on its own. Okay. So you get some weird oddities happening there because you'd be like, I can't kick out an O minus 2. That's where the remnant pieces of our lithium aluminum hydride come in and stabilize that. Okay. It's a tricky piece with the amides, but you're responsible for it. Okay. So to Cassies' question, now that we're pretty darn close, if I start with an acid chloride, can I stop at an aldehyde? Well, if I add sodium borohydride and lithium aluminum hydride, no. I form the aldehyde, but aldehydes are reactive with both lithium aluminum hydride and sodium borohydride, which means it continues to go to the alcohol. When we look at the ester, could I react it to form the aldehyde with sodium borohydride? No, sodium borohydride, not very useful at reducing esters, so sodium borohydride is a bad choice. Lithium aluminum hydride would make the aldehyde, but then aldehydes are reactive with lithium aluminum hydride. So in the quick answer of this is no, we can't stop it until somebody comes along and says, well, actually, what if I play around with those reagents? Okay? And this is where you go, oh my God, that looks crazy. What is going on with those? Okay? This is common for the ACS to do as well. Throw in these weird reagents that you're like, oh my God, I've never seen that. There's no way for me to possibly understand what's going on with that. What is Li? Lithium, which is a metal. Typically what charge? A positive. Okay? Aluminum, ooh, aluminum next to hydrogen. That seems kind of like aluminum hydride. So this could easily be referencing H minus. Then I have this OT butyl thing with 3. That's the remaining 3 hydrogens, but they're now bound to oxygens. So this reagent is really the exact same process as lithium aluminum hydride and sodium borohydride. By looking at the individual atoms, you can piece out where that reactivity is. The reactivity is that hydrogen bonded to an aluminum, which means I've got a hydride source, okay? Which means I should reduce. Well, if I was going to reduce to the alcohol, wouldn't I have just picked lithium aluminum hydride or sodium borohydride? Aren't those easier and cleaner to look at? So wouldn't I want that? Yeah. This says don't go all the way to the alcohol. So what does that mean? Don't use lithium aluminum hydride or sodium borohydride. Okay? If we were trying to find the possible answer for this, if I was given the reagent and I look at that reagent and go, oh my God, that's a mess, but it has a hydride. Ooh, hydride, I'm probably going to do a reduction. But if they wanted me to do the full reduction, that would have been a lot easier to just write LiAlH4 and be done with it. Why the hell did they put all that other crap on there? Because I didn't want to go to the alcohol. This reagent will take an acyl chloride and stop at the aldehyde. Why does it stop at the aldehyde? Because of the rest of that crap that's floating around in there. It's that crap that prevents the reaction with the aldehyde.
If you want an aldehyde, what can you use NABH4?
NABH4 will not stop at an aldehyde. NABH4 reacts with aldehydes, so it will continue to make the alcohol. Sodium borohydride and lithium aluminum hydride react with aldehydes.
You can't stop it.
I cannot stop there.
What if we had sodium borohydride with tetroxide?
So there's an interesting question. Could we go through and modify what is connected to the hydrogen? Could I have boron instead of aluminum up there? Would that change the reactivity? Yes. That will now select for one thing over another. What if I change the temperature? Is that going to change it? Yes. It turns out that there's possible permutations of you can get lithium borohydride. What is that going to do to its reactivity?
Isn't that the same thing as sodium borohydride?
Lithium is smaller than sodium borohydride, which means when I bond lithium to the oxygen, I polarize that bond more, which means the electrophile becomes more electrophilic. By making subtle changes to each of those pieces in there, we can drastically change what it's going to target. Okay? The biggest lesson that you need to get out of this, whoops, was not that part, was that if you see boron or aluminum connected to hydride, do a reduction. The next question becomes is how much should you reduce it? That how much is typically not asked. Okay? If you see something goofy, don't reduce it all the way. Okay? If you see something normal, reduce it all the way. Okay? So that top one has a name, which I think is on the next slide. The bottom one, which is exactly what you're asking about and why you might have been calling it Dieball because of how Carty likes to write it out. Okay, what is the A? Aluminum. Most people actually reference this as Ball because it's Al for the aluminum. Right? So when you talked about Dieball, that's why I balked, because it's Dieball is typically how it's pronounced or written out. Dieball is another special reagent, like that lithium one up there, that selectively reduces esters to make aldehydes. Why? All the other junk, whoops, let's get to the other junk. All the other junk in Dieball helps prevent it from reacting with the aldehyde. Okay? These two reagents, and really Dieball is the only one that's super important, okay? You have to recognize for their functionality. Dieball is important because it will reduce an ester to an aldehyde. Why is that tricky? Can you reduce esters easily? No, those required lithium aluminum hydride to reduce. Here, if we change the structure around, instead of it being fully lithium aluminum hydride, we can actually get it to reduce the ester. Okay? And the ester as a single step, not as a double step. Okay? So the extra conditions, you've got a lot of steric hindrance in both cases. That steric hindrance helps to minimize some of that secondary chemistry. And they're also both run at extremely cold temperatures. I don't know if you actually noticed that. Both of these are run at negative 78 degrees Celsius. Okay? So very, very cold. Just like if we put you at negative 78 degrees Celsius, you don't move much. The same thing's going to happen with these reagents. It limits their motion, which means less side reactions or less continued reactions can happen. Cass?
Sir, just to clarify, NADH4 reacts with aldehydes to form alcohols.
Yes.
Okay. What about the acid chloride? It looks like an aldehyde, the acid chloride, right?
It has a carbonyl, yes.
Yeah. So NADH4 is it selective? Is it selective for acid chloride? Right, that you have right there in that slide.
So when you say selective, we have to be a little bit careful, because when you say selective, you're saying it's the only thing that reacts. It's not the only thing that reacts.
Okay. Will NADH4 reduce an acid chloride to an alcohol?
Yes.
Okay. But it also reacts with aldehydes to form alcohols.
The reason it reacts with acid chlorides to form alcohols is why? What is the very first product when you reduce an acid chloride? An aldehyde. So when you ask the question, sodium borohydride reacts with aldehydes to make alcohols, it is that answer. That's why acid chlorides form primary alcohols with sodium borohydride. These aren't two separate pieces. They're stacked pieces. Acid chlorides reduce with sodium borohydride to make aldehydes. Aldehydes react with sodium borohydride to make primary alcohols. These are continuous things. The issue is that the aldehyde is still reactive. We can't control the amount of sodium borohydride to only reduce an acid chloride. The amount of sodium borohydride that's put in will also reduce any aldehyde that's formed, which is why you can't stop at the aldehyde. The instant the aldehyde's formed, it reacts to form the primary alcohol. That's why when we look at acid chlorides, does it show an aldehyde as a product? No. Why not? As soon as the aldehyde's formed, what happens? It becomes the primary alcohol. They're sequential steps. Okay?
So are we saying that Dieball is another, how are these,
Dieball and whatever the other name of the other one is, because I don't think I wrote it up there.
do they always start like aldehydes?
Dieball, let's see, do I have the name? And lithium triterbutoxyaluminum hydride. Okay, I don't know what the abbreviation is for that one. Both of those are selective. Okay? By being selective, they change the chemistry from the standard pattern. The standard pattern is we start with our acid halide, and we go to or acid derivative, and we go to an alcohol. How do we get to an alcohol? What do we have to pass through? An aldehyde. those reagents all react with aldehydes and ketones because they're still very electrophilic, which means we continue on to form the alcohol. Dieball and the other one are now selective and different because what happens with them? The weird not Dieball one takes an acid chloride and it freezes it and it locks it at an aldehyde. That reagent can't react with the aldehyde. Why not? Steric hindrance and low temperatures. Okay. Sodium borohydride, lithium aluminum hydride, do they have steric hindrance? It's a lithium atom, an aluminum atom, and 4 hydrogen atoms. Is there steric hindrance? Hydrogen is the smallest atom on the periodic table. Aluminum's 13, okay? And then we got lithium, the 3rd smallest atom on the periodic table, okay? Followed by oxygen and then a T-butyl. Is T-butyl a small thing? No. Lithium aluminum hydride is that same structure that's shown right there, except what have we done? Which of those has more sterics? The other one. Okay? This is why having a sense of what the size of these atoms are and what those formulas mean is important. That's why you were asked to draw structures early on in first semester, so that you would recognize those formulas and those patterns now to see those sterics. Because now is when those steric effects come in. Okay? So we get a steric hindrance that's preventing that top one from reacting with aldehydes. Dieball has a steric hindrance, and as an extra added bonus, what's different about Dieball? I think you said it. There's no charge. Dieball doesn't have a hydride. It has an aluminum hydrogen bond, but it doesn't have the formal hydride that the lithium aluminum hydride or the one above does. That means that hydride, that negative hydrogen, is less active, okay, which is going to slow the reaction down. That's going to be one of the reasons why it's going to prevent it from reacting with aldehydes and ketones. Okay? This is where the regardless is. Look for your metal hydrogen bond. Okay? That's the key piece. If you have a metal hydrogen bond, what do you have? You have a negative hydrogen. If you have a negative hydrogen and it's attached to a metal that isn't sodium or group 1s, you're doing a reduction. Okay?
So, you might have said this before, I'm not sure, but I would write this down so I can write it.
Go for it.
Dieball, it only stops at the aldehyde because the hydrogen is not as active,
Yes,
but it's attached to a metal.
it is.
Or
Which is
aluminum.
aluminum. Yes. It is a less active hydrogen. Just because it is connected to a metal doesn't make it the same activity. Why is the activity of the hydrogen in a lithium aluminum hydride more active than a hydrogen in Dieball?
It doesn't attach technically.
What's the difference? As a hint, lithium aluminum hydride is negatively charged. Dieball is not. That's your biggest and huge. Why? It's not. Doesn't have the 4th bond. That's it. It needs a 4th bond to have that, to be negatively charged. It doesn't have the 4th bond. Right? It's the number of things that connected to it.
So you're saying that steric hindrance prevents it from reacting again to aldehyde, but wouldn't
It's a contributing factor, yes.
So wouldn't there be more steric hindrance with what you're starting with? Because the chlorine would be bigger than the hydrogen.
Does the chlorine sterically hinder? Where's the hydride reacting? The hydride is attacking the pi bond, which is above and below the plane of the molecule. The chloride is a secondary feature as far as steric hindrance. Doesn't contribute.
So it looked like the sterogen would also
Yeah, there's lots of contributing factors. Yep. Yep. And you can switch them out. You can have lithium, you can have sodium, you could have potassium, you can have aluminum or boron with any one of those combinations. You can change what ligands, what are these carbon structures that are connected to our metal. Any change there changes the reactivity. Okay? So if you look up your metal hydrides, your aluminum borohydride structures, as far as reagents go, it's not just 4. There's tens of them. And the selectivity of those changes because you're changing those pieces. Okay? Bottom line, aluminum borohydrides do what? Reduction. So do it. Okay? Dieball is an important one. Why is Dieball an important exception? Did it reduce all the way? No, it stops the reduction. The top one also stops the reduction. It just doesn't have as nice a name. They do not react with ketones. Okay. Our organometallic reagents. So we're now talking about negative carbons, just like we did in the previous unit. Negative hydrogens, negative carbons. Where are sources of negative carbons? Grignard. Cyanide. What's that? Enolates. I'll accept enolates. Enolates get a little bit tricky, so I'd leave those off for the moment. The organocuprates, also known as Gilman. Right, so there's a bunch of different places that you can get, negative carbons. How are those all going to react? Okay, so if I start with a Grignard and I attack the acyl chloride, what happens? I break the pi bond. I form the tetrahedral intermediate. I reform the pi bond and I kick out the leaving group. What would I make? In this case, a ketone. Do ketones react with Grignards? Okay. This should not be a question, but that might explain lower scores in the last unit. That is literally what happened in the last unit. That's when we talked about Grignards. What did they react with? Ketones. Right? So if I take an acyl chloride and mix it with a Grignard, what happens? It reacts a second time. Right? That's because I still have that polar pi bond, which is an electrophilic carbon. And I would get another CH3, and I end up doing the substitution multiple times, or sorry, the addition multiple times. So it starts in the first part, beginning to end, as a nucleophilic addition, followed by the elimination to make that product. The next step is a nucleophilic addition. Unit 3, Unit 2. If you have a problem in Unit 2, guess what's going to happen in Unit 3? It's going to multiply. Right? You need to be doing more practice. Right? There's our mechanism for our Grignard reaction. Note it's the same deal. Nucleophilic attack, tetrahedral intermediate. Elimination, nucleophilic attack. Do we have a leaving group? No, so the reaction stalls until we add acid as a workup to put the hydrogen back on. There's my final answer. Okay. As kind of a ballpark idea when looking at these reactions, should you see a carbonyl in your answer? No. Why not? Because it reacts with carbonyls. So as a quick kind of blanket, I'm looking at multiple choice, I don't know what to do, pick an answer that doesn't have a carbonyl. Okay? Majority of the time that'll work. The few cases where it won't are those exceptions that you're told to memorize. Dieball. Okay? We get a slight change when we switch to the ester. Why might we get a slight change when we get to the ester? Which is more active, the chloride or the ester? The chloride is more active because we can make the argument that chlorine is a better leaving group. Remember, that is not technically correct. Chloride can't do resonance, oxygen can. Okay? It is that resonance that limits ester's reactivity. Which of these two would we expect to react faster? The top one. Sorry, no, the bottom one. Why the bottom one? Because it's starting with a more reactive acyl structure.
But isn't,
The ester is less reactive, period.
no, but the reagent
The reagent is a lithium versus a magnesium. You're right, we do get a slight difference in reactivity there, not significant enough to stress about. Ultimately, both of these are going to be incredibly fast because we have a stupid strong nucleophile with a negative carbon. Okay? What would we expect our answer to be in the top? Do we expect anything to happen out here? Why do you not expect that alkene to react? It's a nonpolar pi bond, and nonpolar pi bonds act as nucleophiles, unit 1. Right? Carbon lithium. Guess what that is? A nucleophile. A nucleophile to a nucleophile doesn't make sense. Our nucleophile should attack. We break the polar pi bond. We reform the polar pi bond. Do we have a leaving group? The OCH3, we can kick that out. Is oxygen a good leaving group? I mean, OCH3, I have a negative carbon. Is that a good leaving group? It's more stable than the negative carbon. So yes, that's a bad leaving group. Leaving into a system that has worse leaving groups in it. That's a better thing to happen. Okay? Now what happens? What functional group would I have? I would have a ketone with a bunch of stuff in the double bond. Do ketones react with Grignards? Yes. So what happens? Nucleophilic attack. A negative charge. Now what happens? Protonates. Right? You're following the pieces behind each of these. You have to recognize those pieces. Right? Negative to positive, negative to positive, negative to positive. Look in the bottom structure. What do we have? Oh, I have a Grignard. What do I have in a Grignard? I have a magnesium bonded to a carbon, which means negative carbon. I found a negative. What do I need to find? Where's there a positive? The carbon where the carbonyl is. Why is that a positive carbon? Resonance. Induction. That is a positive carbon. I found a negative and a positive. What should I do? Connect them. If I connect them, I would generate another negative. What would I need to stabilize that negative? Something positive. Where is there something positive? Okay. We have an electron withdrawing effect from that chlorine. We could have these electrons come back down, kick out the chloride. The result, it's okay, a negative chloride. Is that a better thing to have happen? I made my negative more stable. Okay. What's the issue? I have a carbonyl. What can carbonyls do? They could theoretically keep reacting. So I have to be careful with the Grignard reagent to watch out for that balance. Make sense?
Repeat what you said for last.
I have to watch out for my Grignard reagent because my Grignard reagents can react with carbonyls. Chloride was the other thing. Chloride is more stable than the negative oxygen, more stable than the negative carbon. Everything drives that reaction forwards.
It doesn't recognize.
Yes.
Okay. So the-
Okay. What makes these extra tricky? How many Grignards reacted in this bottom case? 2. Does it say 2 equivalents? No. Are you supposed to know that? Yes. It sucks. Deal with it. Okay. Sometimes we're nice and we go like, hey, there's excess. Here you go. Okay. Sometimes not. You're responsible for knowing that continued reactivity. Okay. What we've got here is a Gilman reagent. Okay. Gilman reagents will react with acid chlorides. Would they react with aldehydes? Or ketones? Okay. I appreciate the no. It's a little soft for me, but I appreciate that. That's awesome. I wasn't telling you to shout it out, but that works. The only reason I'm writing that big is because I drew it big. Okay? Those don't react with aldehydes and ketones. Why do the Gilmans not react with aldehydes and ketones?
They're weak. They do 1,4.
They do a 1,4 addition. They aren't strong enough to attack the 1,2. Okay? Why will they react with the acid chloride if they don't do direct additions?
So positive.
Why is the acid chloride so positive?
Resonance and induction.
Resonance and induction. Remember, I had a slide earlier on that showed the reactivity ranking. We start with acyl chlorides, then anhydrides, then aldehydes, then ketones. Okay? Then your esters and acids, then amides, then the carboxylates. That ranking is of critical importance. So that if you don't know that ranking, it makes it very difficult to decide what's going to happen here. This is a Gilman. The Gilman will react with that excessively electrophilic carbon, okay, which means what would we get as a product? What, you can't name that? So we'd kick out the leaving group, right? There's carbon 1, 2, 3, 4, 5, double. What functional group do I have? Ketone. I'd be like, oh my gosh, I'm adding a strong nucleophile to my chlorides. I should be reacting it again. What do ketones do in the presence of Gilmans? Nothing. So if I want to stop the addition, I can switch up the reagent to a Gilman addition, and now it's going to stop at the ketone. Okay? So Gilmans can be a useful selective nucleophilic addition elimination because they won't continue to do another nucleophilic addition. Their reactivity is less. Okay? Okay. One of the things that's kind of fun is they throw in words like generally. Okay? We can throw in exceptions and we can mess with things. Add heat, add a little bit more reactivity, you can almost always mess with it. Okay? We've got our big summary of interconversions again. Notice the aldehydes and ketones are not shown in this, so let's go ahead and insert those in so that we've got that in your notes because it's really, really important to know your aldehydes and ketones. The reason they're not included, why is that? Once I form an aldehyde or a ketone, can I make any one of those species? No. Okay, it is not easy to go from an aldehyde or a ketone to any one of those. We can go from one of those out to an aldehyde or ketone, but it's a separate kind of reaction tree. I can't show how to convert aldehydes and ketones back in. Which is more reactive, the aldehyde or the ketone? Why is the aldehyde more reactive? The carbon of our ketone has more electron density. It can stabilize a little bit better. So our aldehydes are higher in reactivity than our ketones. They come in right above our esters and acids as far as reactivity.
Why are they in the same chart?
What is this chart showing?
Just acid versus
The interconversion between each of these functional groups. Can I convert from a ketone to any one of those? No. Because the chart shows an interconversion, I can't include them in there because they don't interconvert. I can go from some of those out to an aldehyde or ketone, but I can't go from an aldehyde or ketone easily back in.
Is it because the leaving group didn't stay out?
I have to deal with leaving groups, and that becomes the problem.
Okay.
Okay, so we got another spider diagram. This shows all of our acid chlorides. Okay. When we start with an acid chloride, where can we go? Yay! Which of those are you responsible for? All of those. Guess what we're also going to see? Instead of an acid chloride, the anhydride, bromide, iodide, ester, acid, amide. And you have to decide, would each of those reactions potentially branch out from those pieces? How are you going to know that? That comes back to the reactivity of your starting acid derivative. All right? This one's in there is just kind of a random one. We've already talked about these. Okay? When we talked about our sulfates early on in chapter 10, okay? We have the sulfur and we had the bond out, and in the slide I said a squiggly. If the squiggly was an OH, we said that species was? That's right, awesome memory. We said that was a strong acid. If it was a chloride, we said it was? We had a leaving group, was our chloride, and the sulfur was an electrophile. We used it in the circumstance of chapter 10 to convert an alcohol, an OH, into a good leaving group because the alcohol would attack the sulfur. Okay? And then we kind of just ignored the mechanism. What is the mechanism? The alcohol attacks the sulfur, breaking a pi bond. What kind of pi bond? A polar pi bond. So that's a nucleophilic addition. What did that negative oxygen then do? Reformed the pi bond and kicked out the chloride, which is a nucleophile elimination. Beginning to end, what have we done? A nucleophile addition, elimination. Talked about in chapter 10, and here it comes back. Okay, here's the details of that mechanism. I said in slightly different context. Why would we choose to use the mesyl chloride, the triflyl chloride, or the tosyl chloride? Is the chemistry going to be different? Why? I don't quite accept that because they're different structures. The structures, those extra pieces on the end, are going to change some of the chemistry out on the functional group. Why would it change the chemistry? Carbon versus fluorine. What can you tell me is the difference? Electronegativity. So we can look at those differences to help predict how that chemistry would change the group. Depending on the circumstances you're looking at, you might see any one of these show up. The mesyl chloride, for instance, showed up in a lot of the stuff that my research group went through and did. Okay? With that, we've got an exciting